As you're writing this up, keep in mind that I'm reading many of these, and I don't want to read like 30 pages for each of you, so I appreciate brevity. Try to keep it brief. That would be good. Don't feel like you have to put in the kitchen sink. You can put in just the most important parts, and I won't mind one bit. Okay. One of the other logistical issues is, at least it's the first time I've taught this class where a number of people are going to have demos, and those demos involve CUDA, and few people have CUDA on your laptops. So we'd like to be able to have a machine that was here that could run everybody's demo. And so I asked Andrew if he would perhaps do that, and he's tentatively agreed. But what I don't want to happen to Andrew is to like somebody show up 5 minutes before class and have like a memory stick with an exe on it, and then to plug it in, and then what if it doesn't work correctly? Or so I want to talk about that. Who would like to give a demo on Thursday? Okay. What do you need to run it on? No demo. So you lied about the demo.
No, I didn't lie about the demo.
Did I just have you raise your hand to say if you were going to show a demo? Okay, so you did lie.
I'm sorry.
All right.
Just CUDA and OpenGL.
CUDA and OpenGL.
Same here if I don't know.
Okay, moving over here. Any of you guys? Okay.
Will it matter if CUDA is if I compile to 64 bits? AMD, is it going to be?
That's a good question. So, Andrew, are you or is anybody willing to bring a laptop, or what? Can anybody bring something that can easily do this?
What's the requirement? I'm sorry.
I just was curious.
If he did it on AMD 64, was the question. Okay, Andrew, what do you have on your desktop?
I have CUDA 2.0. What do you run? What's your hardware? So it's GeForce 8600 GS.
That's your laptop.
What's the CPU code? It's an Intel. I don't know what the chip is.
So my laptop does GeForce 5800 S on it, and it's Intel Duo Core 2. So if you look at the exe type, it says x86 64. So I move code back and forth between Opera and laptop. But the only problem with this particular GPU is that it just has one
SM.
one processing core.
Okay.
And not very much memory.
Are you suggesting doing it on your laptop then?
Yeah.
Okay. So.
It's not gonna, if you want like super high performance, not going to get it, but it will work.
Okay. And you're running Windows?
Yeah.
Okay.
It's all in Windows.
Never mind. Are you doing Linux only?
Yeah. It's fine. I have it's okay. If I don't demo, that's fine with me.
Okay. I mean, it's
I'm talking about design decisions and just showing screenshots that I have them. So.
okay. I mean, it's like
Or I'll carry my carry some over too.
like demos are great, and everybody wants to see demos, so it's certainly desirable to do it. But it seems like if you're only running on Linux, it's going to be a hard sell to make that work. Okay.
Possible. I think on Linux you can do like a screencast. Maybe you can make a video of it working and just play it over.
Yeah, sure.
Maybe.
So have you done that before?
Yeah.
Okay. So
Sample.
is that the name of the software?
Yeah.
Okay. So it's like the Fraps equivalent. Fraps is what people use on Windows, yeah?
That or
Okay. If you had Windows, would that work for you?
Maybe. I'm doing my development on Linux too. I can plug my laptop in there. I can't run CUDA, but I can sort of get it over the network.
Okay.
maybe able to emulate it on Windows too. I have a Windows laptop that I have CUDA installed. I just haven't, ported the code over or done anything to see if it runs just fine.
Right. Okay. I'm trying to facilitate best I can.
First off, just to clarify, the computer that would be brought in is a Windows
Laptop.
Okay.
Andrew's willing to share that, which is cool. Thank you.
And I think if I'm thinking of doing my desktop, which is GeForce 9800 GT platform.
Okay. Windows or Linux?
That's a Windows, but that's a build to Linux, but I haven't used the Linux, so I'm not sure that
That's fine.
Okay. Any guys besides you two that don't have machines for this? Okay. Sounds like if you're only doing Linux, nobody's going to bring in a machine that's going to work for you. So I guess I'd suggest either bring in the machine if you can, or taking a video, and that would be helpful. It's really cool to get a demo, but don't feel like you should really totally put yourself out over that. Okay. Is there any other demo/talk kind of issues that are here?
So it's going to be 5 minutes, not 10?
I think I said 6. I mean, just counting how many people are in here, that's about right. I'll get to that. Okay, I'm just trying to work out machines right now. Now, for those of you that aren't, okay, regardless, who needs a machine to actually give a presentation on? Okay, so can you put it on like a memory stick or something? Okay, because then we can just leave the next machine up here and then just put it in and do PowerPoint. Are you both cool with that? Yeah. Okay, so whoever, when we make order on Thursday as far as who's going, let's let Wes and Stanley do their, borrow your machine would be useful.
I have one more question.
Yeah.
This stuff is not that kind of like video cable, so I'm not sure.
You don't have VGA?
Yeah, that's a
DVI.
You have DVI only.
Yeah, only DVI.
Is it like this kind of DVI? Can you use this?
Yeah, something like this.
You can borrow mine. If that doesn't work, I would try to put it on a memory stick also, and then we can transfer it if we need to. Okay, or at least the presentation part. Okay, good. Okay, so one of the issues is that we kind of have to fit everything in. I wanted to talk about this first because we have to fit everything in the hour and a half that we have, or the hour and 20 minutes. Okay, so what I'm kind of suggesting is, based on the number of people we have, 6 minutes per person, and we can have about a minute to switch over, and that'll give us just a little bit of slack. What I've seen is that nobody goes short and everybody goes long. Okay? So I'm just telling you that in advance because you don't want to go long and then screw everybody who's coming after you. All right? We're going to have to actually cut people off, and you aren't going to get to finish. So I know none of you want to be up here for a long amount of time. Just practice a little bit to make sure that your thing's going to be inside of 6 minutes. Okay. I'm sort of suggesting that you just do this in 3 slides and only 3 slides. Then you don't have to spend tons of time making slides. But you can give a great presentation with three slides and talk about what you did. This will also be posted, so don't go super stressed. It would be nice to have one machine coming for a demo, but it doesn't look like that's going to happen. But if you are stuck in anything, please mail the class list, and hopefully somebody will be able to help you out there. And if anybody's running anything on a Mac, you're welcome to use my computer because it's got CUDA on it too. Okay. What I'm concerned about is sort of the topic of the class here, sort of impact on graphics hardware, impact on systems, and so on. One thing to consider is that all the people in this class are probably not an expert on what you are talking about because you guys have spent weeks studying this thing, and you're often doing things that are a little more related to your own research. So keep that in mind when you're preparing your talk. You're not giving this for experts in your field. You're giving this for your colleagues. So really concentrate on the high level and results. Don't feel like you have to throw the kitchen sink into the talk and talk about every little bit of your project. Pick a couple things that you think are most interesting. Do a good job on those. That's much better than trying to cover everything and fitting it all into 6 minutes, which turns out to be very difficult to do. Okay. And so the talk, I'll grade that based on effectiveness and work that into the project grade. The write-up, I'll grade on content, so what you have to say in the talk there. So not how it's presented, but what you're actually saying. So I'm concerned, again, with the impact on sort of the things we learned in this class. And it's very broadly construed, so that's good. But what did you learn is important. Okay, so a lot of you learned a lot about the system that you're working on or the problem that you're working on, which is good. And then how what you learn will impact future systems. So sort of some of the things that I had down as interesting here. Okay, well, let's say we're proposing doing a technique in a new way. Well, is it going to take more hardware to be able to do that? What would help you? Okay, how does that affect the hardware? How does it affect the interfaces on the software side? Your technique, how do you characterize the performance? How does it change the performance of the graphics system? Try to quantify this best you can. Feature kinds of things in the hardware. Well, now I'm doing this new technique. What can I do that I couldn't do before? So these are a little bit more graphics-oriented kinds of things. If you're doing something in the graphics system, lots of you are doing general-purpose things. But some of the questions that I'd like you to be able to think about and address in your write-up. And sort of the audience that you should think about presenting to sort of our guest speaker kinds of people, right? So we've had great guest speakers over the last few weeks. If we were to take your write-up and address it to one of those people, okay, who, again, aren't an expert in your particular field, but you want to make them interested in the problem that you are studying. So why is that problem important? One thing that's important in this or any other papers that you write, okay, a very important thing, say what your contribution is, okay? It's really hard for me to look at these papers sometime and tell what you did. So don't be modest about that, okay? I extended this in the following way. I implemented this on the GPU and it hadn't been done before in this way, okay? I did this chunk of work. Make sure that's identified in what you do, okay? And what I'm really concerned about is analysis, not just I did this, but I did this and here's what I learned. I did this and here's how this pushes the state of the art. I did this and it's something that hasn't been done before and it was the right thing to do because of X. Or it was the wrong thing to do and it turned out that this approach really isn't the way that you should be doing things, and if I could do it all over again, I would do it in this other way. Okay? But I want to see that you've actually learned something here. So go deeper than just I did this. Okay. Let's see. So I'm now done talking about project kind of stuff. Does anybody have any questions for me?
Should our paper be turned in as a hard copy to you?
PDF.
Yeah. Okay.
That'll be great. And I was supposed to bring those with the graded stuff today, and that's all still in my office. So sorry about that. Yeah.
So are you going to create another entry under assignment so that there's a bucket for us to code?
Yeah, nobody's tried to turn in anything early on the project. Strangely enough, nobody's done 2 days in advance. Do you have anything else to demoralize the rest of the class with? No, you got that covered. Okay, great. Okay, yes, I will. And bug me if you don't see that in the near future after class.
The first assignment, how are those graded?
I gave them to my mom,
Right.
and she graded them, and she put comments on them. Like a Post-it?
It's just a single number, and that's...
Did she put nothing on it except the number?
Yeah.
Okay, we could give it back to her and ask her for some more comments if you wanted. Most of them had more than just a number.
It's like 2 words and a number.
Oh, see, 2 words and a number. That's good. She only had a Post-it worth of space. I wouldn't stress out about it too much. I mean, nobody did poorly, like horribly poorly. We could take up with her about your writing style. She's pretty tough.
I don't care about the number, but I think I know.
Okay, it was graded on a 0 to 10 scale. So, yeah. Okay, I'm going to spend the rest of the time talking about content. So, any other administrative kind of things?
After class, can those of us who haven't picked up that stuff follow you to
Yes.
your layer and pick that up?
Sure. There's outside my desk, office. There's a little pouch with all these in it. So sorry to 3175 next door. Okay. So what we're going to talk about today is parallelism. Okay. So we've talked about the graphics pipeline being this very parallel machine, and we've seen some ways that it is parallel, and we've seen sort of architectures of the NVIDIA machine and the AMD machine and the Intel machine, and seen how this has parallelism in it. And so why are we interested in this? Well, parallelism helps us run faster, okay, more frames per second, so we can do things real time we couldn't do before. It helps us run bigger problems too. So we can run a small problem in real time. How do we run a bigger problem in real time? Well, as we get more parallel, that may be more capable. The other reason is that parallelism is sort of a time machine. And by that I mean if you build a big parallel machine, you might be able to explore workloads or techniques that aren't going to be in the commodity market for a few more years. So you build this huge cluster and you're able to try all this new cool stuff and learn about how to best support it, and then use that to influence the design of commodity stuff. So in a few years when the commodity stuff catches up with your giant parallel machine, then you're going to be ready to go. Okay, so these are all good reasons to look at parallel kinds of things. So, in any frame, we have lots and lots of triangles per frame. And we can process all of them in parallel, right? They don't depend on each other, and that's part of the design of the pipeline. And we have lots and lots of pixels per frame. Okay? And those are also parallelizable. So, well, what's the problem here? Why am I giving a whole lecture on parallelization when we have tons of parallelism here and tons of parallelism here? What's hard about parallelism?
Finding it.
Pardon?
Finding it.
See, I got to say this is, but you're doing tons of triangles per frame, and they're all parallel, right? Okay. Independent. What do you mean by independent?
They depend on each other.
Okay. They are independent, right? Like, that's the whole design of the pipeline is such that the triangles and the pixels are independent. So, in many applications, it's very hard to find parallelism. In graphics, these two things are both very parallel. Okay? So what's hard about building a big parallel machine if we have all this parallelism?
You might be able to get better results if they had some dependency. Like, take ray tracing, for example.
Okay.
Like, you know how, well, in ray tracing, it's per pixel, which is independent, but then they depend all on the triangles that they hit.
Well, I mean, you have a lot of free... So, I mean, what you're suggesting is scheduling the parallelism is important. And I agree with that. Like, if you want things to be high performance, you'll want to schedule things with knowledge of their locality.
Right. So it's similar to the delay stream that we talked about the other day.
Okay. But but let's think about how that impacts the hardware. I mean, maybe you'll have different scheduling decisions. Okay. What are the problems with parallelizing in this way? What makes parallelizing hard and interesting?
So you have the output of one providing the input to the next one, and so they're not completely separable.
Okay, this is true. So one thing is that these things are this produces this. Okay, that's true. That's true. But a good queuing system should be able to take care of that. This just fills up a queue, and this drains from the queue. Okay? And if you can fill the queue in parallel and drain from the queue in parallel, then hopefully that's not going to be too much of a problem. Okay? What is there about graphics that might make it difficult to have perfect parallelization here?
Load balance?
Okay. Load balancing. So what do you mean by load balancing? This is one of the key ones here.
Oh, so like if all the pixel work piles up in a small region of the screen, then you wouldn't be able to amortize that work across the processors assigned to different tiles. And
okay. So let's say we had 4 parallel pixel processors. Okay, and we said, all right, here's how we're going to divide them up. Okay, we're going to take this whole screen, we're going to divide it into 4 quadrants. Okay, and then I give you a scene so that all the interesting stuff, all the polygons are down here. Okay? Well, then that's kind of bad, right? Because these 3 guys are sitting around twiddling their thumbs. They have no work to do. Okay? So then you're not going to get any parallel speed up at all. You've paid for 4 pixel processors, but you're only getting the performance of 1. So one of the big issues here is that we have to do, so we have a lot of parallel work, but we want to load balance the parallel work. So one of the goals for us in building a parallel system is that if we have lots of different processors, we want to keep them all busy. And it's not trivial to do that. Okay? So if I did what we're going to call a screen space subdivision, where we cut things up and each pixel processor is responsible for a different part of the screen, we'd like to make sure that it's not possible to have these big load imbalances there. Okay? So maybe that's not a very smart way to divide up the screen. Okay? Another graphics problem that we have is ordering. Okay? So we've got all these pixel processors and all these fragment processors. But remember that OpenGL and DirectX and other interfaces require that we do things in order. That if I specify triangle A before triangle B, then all of triangle A's pixels must appear to execute before all of triangle B's pixels. Okay? So that makes things really hard to parallelize. Okay? That's really tricky because now you only have to, you have to keep things in order. Okay? If I give some work over here and some work over here to two different processors, when we put it back together to make a final picture, I have to make sure that the first part of work is going to take effect before the second part of work. So these two problems are really important problems. Okay? When I specify a new piece of graphic state, when I change GL color to a new color, I have to make sure across all the parallel processors that it does not affect the ones that came before me, but it does affect the ones that came after me. So that's very important. Okay? If we want to do frame buffer operations, the painter's algorithm. Okay, the painter's algorithm doesn't use a Z buffer. Instead, I start by rendering the things that are farthest away from me, and then I gradually render things closer. So I've sorted back to front, and just like paint, the last thing I draw is the thing that I see. Okay? So if I get things out of order there, I'm going to have the wrong picture. Okay, but that's a legitimate graphics algorithm there. Okay, rendering to texture, I got to decide, hey, when to cut it off and say that's the texture that I rendered. Everything that came after that, well, I throw it away. Everything that came before that, it has to make sure to take effect. Okay, so ordering is very important. And we have to be able to have a parallel structure that's going to take advantage of ordering. Okay, and some do and some don't. But, sorry, not to take advantage of ordering, to impose ordering, to keep track of it. The other issue is this issue of load balancing that Wes brought up. We say, well, we've got different amounts of work per primitive. Okay, this triangle gets clipped and this triangle doesn't. There's a lot more work with the clipped triangle than the one that's not. And then different positions. They can land anywhere on the screen. And we want to make sure that we're not duplicating work across multiple processors. And we want to make sure that we're not leaving processors idle. Okay? And these are all significant problems. And what it means in practice that if we had one pixel processor and then we raise it to n pixel processors, it's very hard to get n times the performance from that. And these are some of the reasons why. Okay?
So which one are the big graphics companies most worried about?
Which one of these?
Yeah. I mean, is there one that they focus most of their efforts on?
Well, they have to do this. Right? No question. So they do whatever they need to do to make this work. Okay? Then they do the best they can on this. The more balanced it is, the better. It's probably the fair thing to say. And what we're going to look at is different architectures for how to organize multiple parallel things, and then talk about some of them do this and some of them don't. One of them doesn't do this in particular, and then they do a variable job on load balancing. Some of them are really good and some of them are not so good. Okay? So we'll take a look at that here. Okay? So everybody clear on these problems? Okay, these are things we have to solve. These are not easy problems, and I'll be talking for the next 40 minutes about how we solve these, but these are not trivial problems. These are very difficult problems. Okay, so we're going to start off by doing a little bit of terminology. I hope that we'll get through evaluating the taxonomy in 40 minutes. So, but we'll start by talking about different ways that we might think about parallelizing, and then talk about the cost of communication, which is very important here, and then sort of talk about how we classify different ways of parallelization and how we figure out which ones of those are good and bad and why. Okay, so the first thing we want to look at is what do we actually want to measure? Okay, we're trying to do more. We're trying to add processors to do more. And so what do we hope is going to get better? So there's a bunch of things. Okay? One is that we'd like to be able to input more geometry per second. Okay? So sort of what comes into the system. And that's something that affects all three of these. Okay? We want to increase our triangle rate, how many triangles we do per second. We want to increase our pixel rate, okay, or fragment rate. We want to increase our texture memory. If we add more hardware, we'd like to have more texture memory to play with. That would be really good. Okay? And then we'd like to also increase our display resolution. Okay, it'd be pretty cool if we could have twice as many processors and drive a display that was twice as big. So if we build scalable graphics, okay, as we add processors, we want all these things to increase. Okay, that's the ideal case. All these things are going to get better as we add more processors. So we can think of actually solving these problems in two different ways. Okay, one is we add processors and we can process the same input faster. Okay, one is we can add processors and do n times as much input. Okay, so either one of those would be fine. We'd like to be able to do both of those. Okay, but either one of those is fine. So we'd like to increase throughput or decrease latency. Okay, either one of these is acceptable to us. Now, if we add n times as many processors and we have n squared cost, that would be bad, and we really want to avoid costs that are going to be nonlinear. Cool? Okay. Fortunately, we have a lot of parallelism. Okay, there's a lot of parallelism in this problem. Okay? First thing is we've got task parallelism because we have a graphics pipeline. There's a lot of different stages. We can do pixel work at the same time we're doing triangle work. So that's really good. Okay. So besides that, we also have data parallelism. Okay? And several kinds of that. We could calculate 2 frames at the same time. Okay? Frame 101 and frame 102. Okay? And this isn't the way people usually do it. There was a machine called the SGI Skywriter a long time ago, before probably most of you were born, that actually did 2 frames at the same time. Okay? We can have what we call image parallelism. Okay? We have a lot of pixels that we're computing. We can say, all right, you're doing the left half of the screen, you're doing the right half of the screen. We can do object parallelism. Okay? We have a bunch of triangles that are coming in. You take these, you take these. Okay? So that's a lot of parallelism we can take advantage of. And so we want to distinguish between things we can do within a frame versus between frames. And in general, what we're going to talk about today is within a single frame. How do we speed up one frame? How do we make one frame run faster? If we wanted to go interframe, we can take advantage of frame parallelism. But mostly we're going to be doing these 2 things here today. Okay, so to look at what SGI did. All right, so here's how much geometry parallelism do they have? And so looking basically the graph here with time going this way, and number of processors go this way. And so they started out with one processor here did sort of 1/n of the pipeline. They had really weak processors starting out. And they actually made the pipeline deeper and deeper. So they had sort of 1 processor wide, so they only did one thing at a time, but it took many processors to make that work. Over time, they ended up being able to shrink that as the processors got more and more powerful. And then once they got down to doing 1 processor, being able to do the whole geometry part of the pipeline, they started going wide. They had many processors working on many pieces of geometry all at the same time. Okay? So eventually that got up to 8 here and 12 here. Okay? That's 8 processors or 12 processors all working on different pieces of geometry at the same time. So in modern GPUs, you can see the same sort of thing. If before like the G80 class, you got up to like I think 8 geometry processors that were all working together at the same time. If we look at like a G70 class machine. Okay, how many raster or fragment processors did we have? Well, that really went through the roof. I mean, you're getting over 300 fragment processors working at the same time in a reality engine or an infinite reality. Right? So this is showing that they're increasingly taking advantage of more and more hardware at the same time. Okay, so there's one thing I want you to get out of today's lecture. It's the concept of this idea of a sort. Okay? So when we're talking about how to parallelize, how to take advantage of many geometry processors and many rasterization processors, at some point we're going to have to do this structure that we call a sort. So the idea is that we start out in the application and we have input that's parallel in object space. Okay, we have a bunch of stuff. It's out in object space, a lot of triangles to draw. All right. Eventually, when we get down to having many processors working on the image, okay, eventually they're going to put out output that is image parallel. Okay, that's in parallel at the screen. Right. So at some point we have to transition between object parallelism and image parallelism. Okay, to convert between those 2 things. Okay? And we call that the sort. Okay? We have to sort between object parallelism and image parallelism. And it's the point where we communicate work. Okay, so we have a certain amount of work, and it's going to go to a processor that is responsible for a piece of the screen. Okay? So this processor is responsible for the left half of the screen. Whenever we transfer work to that processor, we say that that is the point where we do the sort. Okay, so it turns out there's many places we can do the sort. Okay, one is that we can sort as early as possible in the pipeline. Okay, and this is called a sort first machine. So what we're going to do is we're going to have the application, and it's going to immediately decide where on the screen this particular triangle goes. Okay, before it's done any work on the triangle at all. And then it's going to send it to the right processor. And that processor will do all the geometry phase and then all the rasterization phase. Okay, so this is one way that we can organize things. And we'll look at this in a little bit more detail late in the lecture. All right, but this makes sense. Okay, you have a triangle. You figure out which processor will be responsible for drawing that triangle. Who's responsible for that piece of the screen, and you'll send it to the processor that's responsible for that piece of the screen. Okay. So one question you might ask yourself here is, well, if we haven't even done any geometry processing yet, how do we know where to send it? Right? We have to figure out where it lands on the screen, right? But we haven't even done the geometry stage yet. So how do we know this? And that's why this is a pretty crappy method, right? So it isn't very good because you have to do all this work up here to figure out where to go, and then you do the geometry processing, right? So you're sort of doing redundant work. Okay. So that one's not particularly good. Okay. The next place we can sort is between the geometry and the rasterization stage. So here we have object parallel geometry rendering, right? So you take this bunch of geometry, you take this bunch of geometry, okay? Then when we finish the geometry, we're ready to rasterize it, and we send each piece of geometry, now that we've transformed it, to the rasterizer that's responsible for that piece of geometry. Okay? So I do my geometry stuff in object parallel, and then I send the geometry to the right processor that's responsible for image parallelism. I send it to the right place in the screen, and the processor that's responsible for that place in the screen. Okay? So this is what the Larrabee is going to do. Okay? This is more of a sort middle machine. And this is classically what the SGI machines do as well. Okay? Or we can do what we call a sort last machine. All right? So basically, we're going to take object parallel work. We're going to do everything on that in parallel. Okay? So then I'm going to end up with one sort of partial image, and you're going to end up with one partial image. And then we sort last, we're going to put those images together. Okay? So this is another kind of machine that we can build. Where we don't do any sort until we've already sort of completed the image. And then what this essentially becomes is how to put these images together. Okay? There's more fine-grained ways to classify this, and we're going to look at them shortly. But the really important thing here is that at some point we have to do communication in this pipeline. Because if you have a triangle up here, it could end up at any of these rasterizers. Okay? Or sorry, it could end up in any part of the image space. So you have to figure out how to get it to the processor that's responsible for that piece of the image space. When do you do that transition? Okay, you can do it early, you can do it middle, you can do it late. Okay, and we'll look at sort of what the pros and cons are here. Okay, any questions about that? You can go to sleep now if you only got to get 1 point out of this lecture. Okay, good time to take a nap, because this is the most important thing that we're going to get across. There must be a sort. That sort requires communication. Okay, that's the tricky step. Okay, or sorry, that's sort of the step you really have to get right to make this scalable. Okay, because potentially you could do any communication you wanted here. There's a lot of communication to happen, and it's arbitrary communication. And you could think to build that in hardware would be kind of a tricky thing, right? There's a lot of stuff coming down the pipeline, and it can go anywhere. So you got to be careful about that.
This is referring to like ATI's Crossfire, like two GPU cards, and half gets one GPU gets some work and one gets the other, and then you can buy in the end. Right.
So okay. So let's think about what Crossfire does. Tell me if I'm wrong, because I don't really know this. I think what happened, all right, I know how NVIDIA has one called SLI, and I know basically the way that works. So let me try to explain that. We have a GPU here. Okay, we have a GPU here. Okay, we have a bunch of geometry here. We have the whole scene here, and we end up sending it to both GPUs. Okay, then what we have is a screen. And what at least NVIDIA does is they figure out how to draw a line across the screen so half the work is above the line and half the work is below the line. Okay? And so then this GPU draws above the line and this GPU draws everything below the line. And he can throw out all the geometry that's below the line, and he can throw out all the geometry that's above the line. And if anything crosses the line, then both of them have to do it. Okay? So it's not a great parallel machine because both of these GPUs have to process all the geometry for both, no matter where it lands, because you have to process the geometry to figure out which side of the line it's on. So it's not useful if you're limited by geometry performance, okay, because you're not getting any parallel speed up on geometry. You potentially are getting 2 times speed up on the rasterization or fragment kind of performance because you're responsible for only half the screen. Okay, so it's a difficult thing to classify in this taxonomy because GPUs are parallel internally, and they use an organization, at least NVIDIA's use one called sort last fragment. Okay, then we have an additional sort of image space, I think we call it distribute, that's here. So there's multiple kinds of sorting that are going on there. Does that answer your question, sort of?
Yeah, yeah.
Okay. Okay. So we've got to do a sort, and we're going to look at different ways to do this. Okay. So the first thing we're going to have to think about is how do we exploit object parallelism? We have a lot of objects out there. We want to have a bunch of different processors look at them. All right? So the kind of communication that we're going to have here is a distribute. Okay? We're going to have this big wad of work to do, and we're going to sort of divide it up between different geometry processors that need to process it. Okay. So one of the big problems here is load imbalance. Okay? What happens if processor 4 ends up getting all the hard triangles? Getting all the triangles that need clipping or that have a very complicated shading path or something like that. Okay? You don't know that when you're distributing them. Right? You're just sort of dealing them out in some way. You don't know who's going to be the hard problem or not. Okay? You don't know who the problem children are going to be out of the geometry. So that's tough. So, you know, that's, we'll look at how SGI did it, for instance. Okay? But dealing with that load imbalance is a problem. Another problem that we have to deal with is this issue of state management. Right? So I have, I'm sort of dealing things out in parallel. I have to make sure that every piece of work gets the right state. Okay, so when I say GL color is this, I have to make sure everybody after me gets it and everybody before me doesn't. So coordinating that is tough. And then I've distributed all this work out. How do I put it back into order? Okay, so you've got a bunch, and you've got a bunch, and you've got a bunch of work. Okay, and I gave you your bunch first. You have to make sure that when it all ends up at the end of the pipeline, that your stuff comes before these guys' stuff. So that's a little bit tricky too. So at some point, usually there's some synchronization in the pipeline if you do that.
Does this relate to something that was brought up in the narrative presentation where it said if you want to make the processor effective, the programmer needs to understand architecture so they kind of...
Well, so what we try to do here is we try to have hardware structures that will not make the programmer worry about load imbalance. I mean, that's sort of one of the beautiful things about OpenGL. OpenGL looks to you guys like a serial program, you know, a serial interface. But the hardware underneath can be very parallel. And if you do a good job of these, you don't have to know that it's parallel. Okay? So these are problems actually that we want to solve in hardware so that you as the programmer don't have to worry about them. Okay. So what did the reality engine do? All right, so the reality engine had 8 geometry processors. So it used round-robin work assignment. Right? So it had 8 of you processors out there, and it would give you a piece of work, you a piece of work, you a piece of work. Okay? So, and then it would just do that round robin, just like dealing out cards. So that's a good static load balance, but it doesn't really solve the problem if you end up with a whole bunch of bad triangles. Okay? So it doesn't help with dynamic load imbalance, but it helps with good static load balance. So one of the issues is you have this big triangle strip to do. Okay? One thing you definitely don't want to do is to cut up that triangle strip, okay, and give you a triangle, you a triangle, you a triangle, you a triangle. Because there's shared vertices among these triangles, and then if I did that, okay, and I have this triangle strip here, okay, and I take this triangle and give it to geometry processor 1, and this triangle and give it to geometry processor 2, and this triangle, and if I give it to geometry processor 3, then I'm having to do that vertex 3 times, one for each of them. So that's bad. On the other hand, what I don't want to do is take this giant amount of triangle strip and give it to the first guy, and then you get a triangle, you get a triangle, you get a triangle, you get a giant triangle strip, you get a triangle, you get a triangle, right? So that's really load imbalanced. So that's sort of our trade-off here. So what this particular hardware did was that if you got really big strips, it would cut it up into smaller strips. So everybody got a strip of reasonable size. And then ended up having fairly good load balancing sort of thing. Okay, so that's sort of the issues that they wanted to face there. With the next processor, which was infinite reality, they went from doing round robin to doing a least busy method. So they every time they had a new piece of work to give out, they looked around and said, okay, here's the least busy processor. Okay, we'll give it to him. So that was a little bit better at dynamic load imbalance. Okay. Then if we have image parallelism, how do we take advantage of that? All right. So what we want to do here is to say, well, we got a bunch of image processors. What we'll do is we'll give each of those image processors a different piece of the screen. Okay, so maybe we'll divide it up into 1, 2, 3, 4. There's different ways that we can do it. All right? So we have to know where the work is on the screen to be able to do that, to send it to the right processor. So the questions that we want to answer are, do we have a partition that's fixed at the time we build the machine, or do we let that partition change? Okay? Is one processor always responsible for this chunk, or could it be other processors depending on circumstances? And then how big are our chunks? We could go from like every other pixel to big tiles. So generally, the partition that we have here is usually called tiling. How big are our tiles? So we have sort of two choices to do this. One is an interleaving approach, okay, where if we had two processors, you get basically every other pixel. Okay, so it's a very fine-grained approach. We call that interleaving. Okay? We can also have a tiled approach where we have a big chunk. Okay, so every other processor gets a big chunk. Okay. So if you're doing this statically, okay, so at the time you build the machine, and you have little tiny tiles, then we're going to call that interleaved. If you have big tiles, then you're going to have that tiled. Now, if you do this dynamically, okay, it's way too hard to allocate every pixel on the screen to a different thing. So that pretty much implies that you're going to do some sort of tiling kind of architecture. And then you only have to allocate big chunks of things, and it becomes a more tractable allocation problem. Then you could have either fixed size tiles that are always the same size, or variable size tiles, and they can change in size. So there's different approaches we can take. Basically, they're all going to boil down to either doing a tiling kind of approach or doing an interleaving kind of approach. Okay, so the question is, which one of these is better? All right? So what's a good thing about tiling? Okay, why might we want to do tiling?
You have less context switching. So for a lot of small tiles, you'd have to keep switching between different types of data probably. And then
okay. So the bigger the tiles, you're doing a big chunk of work at the same time, and so you're not going to have so many chunks of work to do, and the cost to switch between tiles might be significant. Okay? Okay, what else is good about tiling?
Good memory locality.
Okay, and why does that help you? So first we have the good memory locality for doing something like a text string sort of thing.
Yeah, so like, so when you do memory writes, you're doing a bunch of memory writes to sequential locations, so presumably those could be done with, one write call, some DMA kind of thing, versus, over here where you're, okay, write a pixel, okay, write a pixel. And, yeah. Okay, so more coherent kind of memory writes over here. Okay, so let's say I had a triangle. Okay, triangle of, relatively decent size. Okay, like a triangle here. Okay, that's kind of cool because the triangle all fits within one tile. I can send it just to that tile. Okay, what if I have a reasonable sized triangle and I send it over there? Okay, kind of has to go to everybody. Okay, and that's an issue. So if most of your triangles only land in one tile or maybe two tiles, okay, if they cross tile boundaries in either one of these, you have to send them to every place it crosses. And so there's some potential overwork that goes on there. So, but if you have tiles that are roughly the size or bigger of your triangles, you've got a good chance that when you send a triangle to a tile, it only lands in that tile. So it's sort of a one-to-one communication. That's good. Okay, we like that. It implies that the tiled approach is better for that, that you don't have to broadcast to everybody. Instead, you can just communicate to one guy. And then there's no overwork because only one tile does the work. Okay, here if you send a triangle to this guy, everybody has to do all the per triangle work, like triangle setup. Okay, so that's a couple advantages to tiling. What's good about interleaving? Great load balance.
Okay, interleaving is good because of load balancing. All right, what happens in a tiled architecture if all your work lands in this tile? Okay, well, that tile's kind of hosed, right? Everybody else is waiting around for that tile to finish. It's really hard to do that in an interleaved architecture. It's hard to put all the work in like a 1 pixel square there. Okay, so this is something that load balances very, very well. So that's sort of the trade-off that we're looking at, and different things give you different approaches. If you really care about load balancing, then small tiles are very important. Okay, but you're going to have more overlap. Okay. So you're kind of going to have to broadcast every triangle to everybody because now you've interleaved so finely. Big tiles are great because you can get some more locality there. On the other hand, you've got load balance issues if you're dealing with big tiles. So that's sort of your trade-off, this locality versus load balance, this communication broadcast versus one-to-one. Okay, so you can actually mathematically figure out like how much you can look at sort of the size of a tile and look at the size of your triangle and figure out sort of what the overlap factor is, basically how many tiles you expect to hit for a given size of triangle. Okay, so there's a nice mathematical way to do this. It's kind of cool. Okay, but the overlap factor as your tile gets smaller, and these are things that we've looked at, scenes that we looked at early in the class, as you have smaller and smaller tiles, the overlap factor gets more and more. So you can kind of expect that. Now, we heard a little bit about the issue of switching between tiles. What we're looking at here is how big should our tiles be and how much is our rasterization cost? So these are frames from a software render that was done at Stanford called Argus. So what we're looking at here is we got a bunch of CPUs and they're each doing image kind of work here. Okay? So up there we have really big tiles. Okay? So how long does it take to finish? Well, you have to wait for your longest guy to finish, and you look and there's an enormous amount of load imbalance here. Basically, we've taken the screen and we divided it up into just a few big tiles, and it turned out most of the work was in CPU number 2. So everybody else is waiting around for it. Okay? As we make the tiles smaller and smaller, okay, the load imbalance gets better and better. Okay, meaning that it's going to take roughly the same amount of time to finish everything, so that's good. But on the other hand, we have switching overhead. Okay? It costs more to switch between tiles if we have more tiles. And we're going to have more overlap, and that's going to cause us more work to do as well. Okay? So in this particular render, one of the big things was how big should the tiles be. And if you looked at this particular scene, you would say that a 128 by 128 tile is going to let you finish the fastest, that there's bad effects on both sides of this. Okay? So when Matt came out and talked about Larrabee, okay, they're interested in doing this as a tiled architecture. What they're going to do is take a bunch of polygons in, they're going to sort them into buckets, is what they call them, and each bucket will be associated with a given tile, and then each one of their cores is going to work on a tile by itself. Okay, so just that core is going to work on just that tile and have only the geometry that intersects that tile, and then you're going to have many, many tiles working on many, many cores across the machine. Okay, so they have to be very careful on how big these tiles are because they want to maximize load balance, but they also want to minimize overlap. And so there's sort of this push and pull between those two things. Okay, so we're going to have to communicate. Large tiles, bad load balance. Medium tiles, good load balance. Small tiles, more overlap. Okay, so we're going to look at different kinds of ways to communicate. We're going to zip through this pretty quickly. So we talked about the sort. That's how we go from object space to image space. Okay, and that's important. So that's sort of the core communication that we're going to do, but we're also going to do distribute. Okay, so how do we do object-to-object communication? And we're going to do routing, which is image-to-image communication. And so as we look at different architectures coming up, they'll all have a sort, but some of them also might have distribution and routing. Okay. So these are the communications that we want to be able to do. All right, we'd like to be able to have one processor talking to one processor. We'd like to be able to do some sort of broadcast. We'd like to be able to do some sort of reduction, and we'd like to be able to do all-to-all kind of communication as well. And so one thing I want to emphasize is okay, so you already got your big picture point that you have to sort. Your second big picture point is that if you're doing communication, one-to-one communication is the way to go. Okay? Electrically, technologically, based on technology trends, doing one-to-one communication is very important. Okay? And more and more we're going to see that being the goal. It's much more expensive to do broadcast kind of communication than one-to-one communication. We want to build things that go one-to-one. Okay, so one way we can do communication is a bus. Okay, and so a bus is basically this electric medium that everybody gets to listen to and one person gets to talk to at once. So this room is kind of like a bus. The air is the shared medium that we all have. One person can talk at once, but all of you can hear at once. All right. So a bus ends up scaling poorly. Okay. If you want to have a lot of things communicating to each other and everybody wants to talk to another person, it ends up scaling as n squared. It ends up being very good at broadcast. Okay? I do a good job at broadcasting to each of you, right? I can talk and you all can listen. But what it's really bad for is if each of you want to have a conversation with every other person. Okay? Okay, Stanley wants to talk to Will, all right? And Wes wants to talk to Andrew, and so on. And so you can't really do that at once because there's only one shared medium. So buses scale poorly. You'll have to wait for somebody else to talk to. Okay, so we're moving away from buses. Okay, in general, a bus is not so good. Buses don't run fast. Electrically, they behave poorly. And the scaling is bad. As we scale the machine, we'd really like to not have buses in it. Okay, another type of communication we can do is a ring. Okay, we have a bunch of things that need to communicate. We're just going to hook them all up in a giant ring. So a ring's nice because it's a little bit cheaper. And so if we look at ATI, talked about their big memory ring that runs outside of their chip. Intel is going to have, Larabee's going to have this big ring structure internally for how things travel between cores. So it ends up being scalable. Okay, it's order of n as you add more things to the ring, because all you have to do is cut one line, put something else in, and tie it back together. Okay, it works pretty well for broadcast. If everybody wants to broadcast, okay, then you just sort of slide them all the way around. They're sort of pipeline that way, and it's really good to talk to your neighbors. Okay, if everybody wants to talk to your neighbor, you can make that work all at the same time as well. Okay, and sort of the final one that I'll mention is this multi-stage interconnection network here. And so this is a way to do arbitrary communication from anything to anything else. It ends up scaling as n log n. Okay, but in general, that's a cost we're probably willing to pay as we scale things up. And so pretty much your switches, if you go buy like a switch that has many ports on it, then it's usually going to use some sort of element like this. So we have this little butterfly element over there that can either switch communication or pass straight through. And you can use many of those to sort of make stages and be able to communicate from anything up here to anything else down here. So this whole effort is, it's usually called an interconnection network if you study it. And if you take, I think, 272, you guys talk about that in 272. But it's an interesting area of research. And so the question is, how do we build things that allow anything to communicate with anything else? What we really like is one-to-one communication. Okay? And where many people want to do one-to-one communication with anybody else. And this is an attractive way to be able to do this. Okay. So here's the taxonomy that we're going to talk about. And then we're going to spend 10 minutes just sort of doing this whirlwind through different machines that use different places in this taxonomy. Okay. So we have all these stages in this taxonomy, and where do we do the sort? And what Eldridge had was 4 places where we could reasonably do the sort and talk about building machines. Okay, so one of these is sort first. You're sorting as early as possible. Okay, one of these is sorting middle. Okay, where you sort between geometry and rasterization. This is what Larabee's going to do. Okay, one of them is sort last fragment, and this is closest to what a modern NVIDIA or ATI GPU does. So you're sort of sorting at this highest bandwidth point, but there's some neat things about sorting at this particular point. Or you can sort at the end, okay, sorting right before you display. So there's sort of 2 kinds of sort last, okay, where you're sorting fragments or you're sorting images. And so, again, we're going to whirlwind go through these with like 2 minutes per structure here. So here's what we want to think about as we look at these different architectures. Okay, one is rasterization load balance. So what we're saying is, okay, we have different rasterizers that are responsible for different pieces of the screen, do they all get the same amount of work? So in general, with tiled architectures, the answer is probably going to be no, because one tile might end up getting screwed. With interleaved architectures, probably the answer is yes. Okay, we don't like broadcast communication. That's expensive to do. We really want to do one-to-one communications. We're trying to avoid structures that do broadcast communication. Okay, temporal load balance. All right, well, we might have things statically balanced across the whole screen, but what happens if we have a bunch of work in one place at a time? Is that going to screw us? Is everybody else going to be sitting around and waiting for that? Okay, even if it's evenly balanced over the whole frame. And the final thing is ordering. We like having ordering. It's necessary if we want to run OpenGL or something like that. So we want to be able to have structures that do that. So these are things that we want to think about as we're looking at different architectures. Okay, sort first. So here's what we're going to do. We're going to have the sort as early as possible. All right, we go in, we immediately look at every primitive, and we figure out where is that primitive going to land on the screen. All right? So then we're going to take those primitives and go through some sort of sort step and send them to the processor that is responsible for their place on the screen. The nice part is we're going to do this tiled. Okay? So every rasterizer, every one of these processors is going to be responsible for a big chunk of tile on the screen. So that's a one-to-one communication. We're going to take every piece of geometry and send it to one place, either here or here, hopefully, depending on overlap. All right? Okay, so here's a machine that uses this. This is the Princeton display wall. So this is the way we're going to do it. We're going to have a bunch of PCs. Okay? Each PC is going to drive one projector, and we're going to have this 4x2 wall up here. So what you immediately do is you figure out right at the beginning, okay, which PC is going to get my particular piece of geometry? Which projector is it going to end up landing on? And you send it to that processor. And then that processor runs everything else. Okay? You can also do this with arbitrary screen decomposition. You don't have to map one processor to one. It isn't just one giant tile. You can sort of do arbitrary tiling. The really nice thing about this architecture is that none of this gets broken anywhere internally, so you can just use an off-the-shelf GPU for everything in here. If you wanted to build other kinds of machines that split in the middle, today's GPUs aren't good because you don't get to split it in the middle. You can't split a GPU and say, oh, I just want out all your pre-rasterized triangles. It doesn't work that way. Okay, so you're probably doing extra work to do screen space position. You do have scalable communication. You will have rasterization load imbalance because any tiled machine is going to have rasterization load balance. But you do get to use a commodity graphics processor, and that's a big plus. You don't have to split it in the middle. Okay, this is the most uncommon way people have built things. Okay, and the reason is you have definite load imbalance because stuff lands on the screen in tiles, and this sort is really early to do it, and you've got all this extra communication that goes on there. It is a good architecture for display walls, though. Okay, sort middle interleave. So this is the historic SGI machine. So here's what we're going to do. We're going to have we're just going to take the geometry, divide it all up, and then we're going to figure out, okay, take your piece of geometry, and here we're going to have interleaved tiling. Okay, so every processor is going to be responsible for like one stripe on the screen. So every piece of geometry goes to every processor, and that requires broadcast, and that is an expensive thing to do, and that is the worst part of this particular machine. But then you have fine interleaving, so the load balancing in the rasterizer is perfect. Okay, so SGI basically had a rasterizer that was responsible for one for this pixel, one for this column of pixels, one for this column of pixels, one for this column of pixels, and so on. And so if you look at their machine, okay, these fragment generators, so here we have 10 fragment generators, so each one of these is responsible for every 10th scan line of pixels going down. Actually, they did two pixel columns in parallel. So each one of these would be responsible for 2, and then 2, and then 2, and so on. Does a very nice job of load balancing. That's the good part. Both static and dynamic. The problem is that this sort step is very expensive. You have to build a bus here. And so what they ended up doing is this gigantic bus here. And they spent a lot of money to have a bus. And they basically build a bus as big as they can support in the machine. Okay, they say, we want to get up to this level of performance. And they pay for that bus up front. So that's an expensive thing to do, but it is the only really bad part about this sort middle kind of architecture. Okay, sort middle tiled. So now instead of sorting to an interleaved architecture and having to send it to every single rasterizer, what we're going to do is we're going to tile the screen instead of interleaving it, but we're still going to do the sort at the same place. Okay, so instead of sorting to particular stripes and sort of broadcasting, we're going to send it only to a particular tile. This is what Larrabee is going to do. Okay, Larrabee buckets everything and does this sort step to take the bucket and give it to the right processor that's going to handle that particular tile. Okay, so we looked at some UNC machines there we don't have time to talk about. The nice part about this is that it has point-to-point communication. Right? You only have to send to one thing instead of having to broadcast to everybody. So you don't have to build this gigantic bus there. The bad thing is that there ends up being dynamic load imbalance. So what happens if you have this big, complicated object and it all goes into one tile? Okay. Well, that's going to, everybody else is sitting around waiting for that tile to finish. Okay. Current GPUs do a structure called sort last fragment. All right? Your GPU is responsible for everything up here up to the point where it outputs a whole bunch of fragments and needs to do fragment operations. So things that so here is the fragment stage that you do fragment pipeline, but you've already rasterized into fragments. All right? Then when you do the sort, okay, there's no overlap because the fragment is only the size of a pixel, and that's really good. And so you can do fine interleaving here, and you're not going to have any load balancing sort of things. The problem with this is that this is the highest bandwidth in the entire graphics pipeline. So you have to build something really buff to be able to handle this sort of thing. But you can do that on chip fairly well. So one of the other issues is dealing with ordering. Okay, it's hard to deal with ordering if you end up doing this. Okay. The final thing we're going to look at is a structure that's called Z composition. So here you're going to say, well, I've got two processors. I'm just going to give half the geometry to each processor. Okay? And I'm going to go down and I'm going to store not just the color at every pixel, but also the depth. And then what I can do is composite these things together and build that. Okay? So we do everything in parallel starting out. They don't communicate at all until they produce a final picture, and then we're just going to put the pictures together. Okay? So what's the disadvantage with this? Okay, this seems pretty cool, right? Very nice scalability.
Works great if everything's opaque.
Okay, so this fundamentally fails with what problem?
Transparency.
Transparency. Okay, so what do we not respect when we build it this way? Ordering. We can't build this as an ordered triangle, right? There's no way to know if this pixel came before this pixel. Okay? And if he has two transparent things at the same pixel and he has two transparent things at the same pixel, you can't ever put them back into order so that you go back to front kind of ordering. Okay? So this is a neat architecture, but you can't run something like OpenGL on it. It does not have ordering. So if you're dealing with things that are opaque only, this works out very well. If you're dealing with things that have transparency on them, then you are not going to get the right answer out of that. Okay? But we call this sort last image composition. One of the really nice things is that, again, just like sort first, you can use commodity GPUs because you don't break it anywhere in here. Okay, you don't require any communication. You buy two GPUs, they're both going to spit out a picture, and then you have a piece of hardware that's going to put those pictures together. Okay, so you can build this very efficiently with a ring interconnect at the end. You just have a whole bunch of pixels, and then you just send them all around the ring as they're being produced. And so somebody just grabs them and accumulates them at the end. So UNC had a machine called PixelFlow, and so it had this image composition network that was done as a big ring bus. That's sort of the famous one here. One project that was done when I was at Stanford was called Lightning 2. Basically, you had a whole bunch of GPUs sending in their own images here, and coming down the screen, they would composite them all into different DVI outputs here for like a big display wall. This is roughly a life-size board. It is the biggest circuit board I've ever seen in my life. Okay, it was enormous. Okay, so those are like big FPGAs right there. Okay, so the thing was, I mean, literally about that big. So it was a pretty cool project. Okay, so you've got some load imbalance issues when you do that. Same imbalance that you have as sort last fragment. The ring interconnect is good because it's scalable, but the problem is that you run out of ordering there. Okay, so I hope you understood the sort part, that that's a necessary thing. One thing I do want to put across is that doing one-to-one communication is very desirable. It's expensive to do broadcast communication. You'd like to have structures that do one-to-one communication as much as you can. And then within that, there's a lot of different ways you can organize a parallel architecture. And what's really important is where you put this sort. Okay? One of the fun things about Larrabee is that you're going to be able to do in software any of these kind of architectures. It'll be pretty cool to compare them when that happens. But when Larrabee says that they're going to do a sort middle tiled kind of renderer, okay, that makes a lot of sense given the architecture that they have. But given that technology changes very much over the years, you might see that change as a function of time as things get cheaper or more expensive. Okay, I'm finishing right on time, which is good. I'll put these slides up on the web, and it'll have the the guidelines for the project, and I will see you guys on Thursday.